Hello, and welcome to a digital mathematics lecture for Salt Lake Community College. In this video, we're going to be going through the second part of Chapter 8, describing data. Here, we're going to be talking about the different values that you can calculate to summarize the data instead of summarizing data using a graph. Specifically, we're going to be measuring the data by describing both the center of the data and the spread of the data. First, we're going to be talking about the center of the data. So that's what we're going to be describing here first. And to describe the center of the data, there's three main ways of doing that. And the three different values you may have heard of before. And that is mean, median, and mode. Median and mode. Now the mean of your data, this is also known as an average. So the average value you have, maybe the average height of individuals, or the average number of people that eat Spam every day. I don't know. Something like that. That would be what we call an average. And there's a few different averages. Specifically, this is going to be the arithmetic average. And the way that we calculate an average is using the following formula, which is going to look a little bit more complicated than it really is. To find the mean, we represent with either x bar or maybe mu. These are two different letters we use to represent the mean. X bar, sometimes you'll see mu is usually for a population mean. This is the Greek letter mu. Sometimes you'll see that as well. Either way, to calculate it, what we're going to do is take the sum, that's what this letter means, this is capital sigma, that means the sum of all of your values, all of your individual values, and then divide by n. So this is the sum of all values divided by n, which is the number of values. That's how we would find the average. For example, say if I had the numbers, just make a quick, easy example. Say I have 2, 4, 6, 8, 9, 11, and 14. Something like this. Well, what I would do to find the average is take all these values and add them all up. If I add all of them up, I get 2 plus 4 plus 6 plus 8 plus 9 plus 11 plus 14. My calculator should equal 54. And I divide by how many there are, which there's 1, 2, 3, 4, 5, 6, 7. So 54 divided by 7. If I do 54 divided by 7, what I get, is approximately 7.7. So I guess an approximate value for the mean here. Now, if you notice, that does represent the data roughly. It represents kind of the center. If I look at this data, it's representing a number down here. The reason why it's not as much higher, it's not between 8 and 9, is because I do have values like 2 and 14 that are influencing it, but that number 2 is a lot different than a lot of these higher values. I do have a lot of numbers between 8 and 14. They're kind of higher, but 2 is really different from that, and so is 4, really. So these numbers are really influencing the mean and bringing them down, which is going to be a common theme of the average itself, that if you have really different values that don't really seem to jive with the rest of your data, that will likely pull the data or pull the mean down or up in those directions. I had actually an example of this in my career where I was analyzing YouTube data, and I looked at the average age of YouTube users. And when I took a large sample of YouTube users, I ended up finding an average age of, I think it was 47 or 48. Which seemed really strange to me. That seems like an average age of just people, not really YouTube users. And when I looked deeper into the actual data, what I found was that there were a lot of people that said that they were over the age of 99. That way they could watch age-restricted videos on YouTube. However, that really influenced my data and brought the mean up way higher than what it should have been, which was in the late 20s, early 30s. That's more of what I expected to see. There's always a danger that you need to check the data just to see if you have any weird or outliers that are influencing the data. But that's how we calculate a mean. The median is also known, I'll try to separate these. The median is also known as the middle. It even kind of sounds like that, median mode or median middle. So it has that kind of beginning, and MED, mid, it kind of even sounds like that. Now, to find the middle of the data, there's a couple different ways. You can either use your fingers, which some people do for small pieces of data like this, and they'll just knock off a piece of information from both sides. So they'll note, okay, it's not this one, it's not this one, and then go to in, and then keep going to in until you get to the one that's directly in the middle, and that being your median. However, there's a much more sophisticated way of doing this, which is better if you have larger information. And the way to do that is to find a locator. Now, the locator number is going to tell you where in the data you should look. And for the median, what you want to do is take the number of values you have and divide by 2. That literally cuts it directly in half. And then what you want to do is round that up. And there actually is a mathematical function to do that, or a way of representing that, and that's doing this. Looks like parentheses or brackets, but without the bottom. This is called a ceiling function, which says round up this number. Now, when you do that, you have a couple different things to check. Well, I'll say really, when you do n divided by 2, if n divided by 2 is a decimal, so if it's a decimal, then you use n divided by 2. So you use the ceiling function. If n divided by 2 is a whole number, what you'll do is take an average of both n divided by 2 and the one above it. So you'll average n divided by 2 and n divided by 2 plus 1. Kind of a weird way of saying that. Now, an example of that, because that seems kind of strange. We already did this example where we had the median just end up being the number right in the middle, 8, so easy peasy. So let's make a new data set. Let's make, say 4, put a dot down there. 4, 6, 7, 7, 8, 10, 12, 19, 34, 6, 7, 8, 9. Let's put also 50 in there. All right, so say I want to find the median of this data set. Well, all I'm going to do is count how many numbers I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So if I find the locator of the median, which is 10 divided by 2, should be right halfway between, that gives me the 5th number. Now this is where I look at the two different modes for my locator, for mode 1 and mode 2. If my locator is a decimal, then I would round up. However, the locator is not a decimal, it's a whole number. In that case, what I'm going to do is average that number and the one above it. So that means I'm going to average the 5th number and the 6th. And then cut that in half. That would be an average. Here, the 5th is 1, 2, 3, 4, 5 is 8. So 8 plus the 6th number, which is a 10. It's the 6th number in row. If I add those together, divide by 2, it's 18 divided by 2 gives me 9. That would be my median. Look at how well that describes the data. Yeah, 9's not necessarily a piece of information from the actual data set, but that's fine. It still is really close to a majority of the data. This middle half of it's really good. Doesn't really do too well to describe these numbers up here, this 34 and 50, these really strange numbers. But what that is also showing is how resistant a median is to these kind of strange numbers. This high number of 50 doesn't really do too much to influence the median. Even if I increased this and said it was 500, the median still would be 9. It still would only care about these numbers in the middle here, not this really high number. Same thing if I changed this 4 to a negative 24. It still would have a median of 9. The mean, however, would always be influenced by these really low or really high numbers. So the mean would get influenced by a lot by these values. Which is why we talk about both of them. Mean is really good for a lot of data and to hopefully show if there is skew in the data is what we'd call it, or weird data pieces themselves. And the median helps represent the middle of the data that isn't really influenced by these large values. That's how I was able to tell with my data sets, with the YouTube data sets, why the mean of 48 years old seemed strange. Now, those are 2 measures of center. There's a third one called a mode. And the mode represents the most repeated. That's what we mean by a mode. And the mode is, again, just the most repeated, but it can have a few different options. You can either have a data set that has no mode because you don't have any repetitions. For example, if I just have the data set 1, 2, 3, 4, I have no repetitions here, so there's no mode. I could also have just one mode, like I do in this data set. Even with the adjusted negative 24 and 500, I still only have one mode. My mode here is 7, because 7 is repeated, and it's the most repeated. I don't have anything else that's repeated more than that. So I have one mode. I could have also multiple modes. And I would have multiple modes if there is a tie between values that are repeated the most. For example, if this 12 here was changed also to a 10, then I would have an instance where I have multiple modes. I'd have 2 7s and also 2 10s. I have 2 numbers that are tied for being repeated the most amount of times. So I would have 2 modes in that case. So that's how you find a mean, median, and mode. The first 2 take a little bit of calculation. Mode, you basically just need to look at the data and see if there is one. Now let's look at a couple examples. Again, I recommend pausing, seeing how you do on these, and then unpausing and see how you did. All right, so the price of a jar of peanut butter at 5 stores was these 5 numbers, and we were going to find the mean and also the median. Later on, we're going to find something else with this data, so keep this in mind. Now for the mean, what we're going to do is take all 5 of these values and add them up. So 3.29 plus 3.59 plus 3.79 plus 3.75. Notice that it's non-numeric order. I see that there. And plus 3.99. And I want to divide that by the total amount of values, which there are 5 of. It even says that in the description. So let's find what these are. I'm going to first find what the sum of the top is, so I don't work too quick here. Don't make a mistake. 3.29 plus 3.59, 3.79, 3.75, and 3.99. And what I get is 1841. If I divide that by 5, what I get on average is about 3.62. I get 3.6 or 682. I get 3.682, but I'll just keep it to 2 decimal places because we're dealing with money. So that would be my average. Now, if I'm looking for a median, this one you could probably do just visually, but we're going to be a little bit careful here. First, what we want to do is make sure that the numbers are in numerical order, because the median needs to be the middle number in an ordered data set. This is not ordered yet, so we need to put it in order. My lowest is 3.29. Next highest is 3.59. Next highest is 3.75. Next highest is 3.79, and then 3.99. If I find the median, I would take the amount of values, which there are 5, cut that in half, and what I get is 2.5. Since my locator is a decimal, I'm going to round this up to the third number. And the third number in my data set is 3.75. 1, 2, 3. It is very important to always order your numbers. In this case, they were not ordered. I had to flip these. Otherwise, I would have said 3.79 was my median, but that's not an ordered data set yet. So you always need to put in order first. So that's how you calculate a mean and median. Now we're going to come back to this data set, so keep in mind the 3.68 mean because we're going to use that in a little bit. One more though before we go into how we can measure spread for data. We have here reviewers were asked to rate a product on a scale of 1 to 5, and we want to find the mean, the median, and the mode. All right, so we need to find all of these. However, the data that we have presented is in a frequency table, which may seem a little bit strange. Now, you can deal with this a couple different ways. You can either just order all these out by saying, all right, well, there's 4 ones, so 1, 1, 1, 1. There's 2, 8, or there's 8, 2, so 2, 2, 2. But that gets very monotonous and kind of hard to work with. We should be able to just use the data here. Now, if I had the data listed out, if I was going to find the mean, what I would do is add all of these up together and then divide by how many there are. Well, if I did 1 plus 1 plus 1 plus 1, that's the same as just doing 1 4 times, or 1 times 4. If I also added 8 2's, that's the same as doing 2 8 times, or 2 times 8. So this frequency table can actually help us summarize this data a lot faster. And that's how we're going to solve the rest of these. So 3 times 7, 4 times 3, and 5 times 1. And then we're going to divide that. So this is our mean. We're going to divide that by how many numbers there are. If I do 4 plus 8, that's 12, plus 7 is 19, plus another 4 is 23. So if I do all those values and then divide that by 23, I get, that's 4 plus 16, so 20, 4 plus 16, so it's 20, plus another 21, so 41, plus another 12, so that's 53, plus another 5, so that's 58. And if I do 58 divided by 23, I get approximately 2.52. So that'd be my mean. All right, so that's the first one. Now the median, again, we should also be able to use a locator number. And we already know how many values there are. There's 23. So for my locator, I'm going to do 23 divided by 2. If I do 23 divided by 2, what I get is 11.5. Since that is a decimal, what I need to do is round that up, and I get a value of 12, meaning I need to look for what the 12th number is. Now, this may be harder to do because it's not listed out in order, but what we need to do is consider what this frequency table means. So this 1 and a frequency of 4 means the numbers, the first, second, third, and fourth values are 1s. And then the next 8 are 2s, and the next 7 are 3s. So we can count up to the 12th using this frequency. With the first 4, I haven't gotten there yet. So I keep going. If I go up to 8, it gets up to the 12th number, which is what I'm looking for. The 13th number would be a 3, all the way up to the 19th number. That'd be 7. So just progressively adding these together, 4 plus 8 is 12, plus 7 is 19, plus 3 is 22, plus 1 is 23. Trying to see where the 12th would lie, and it's going to lie within the 2s. So the median is a 2. Furthermore, if I find the mode being the value that's the most repeated, looking at my frequency table, 2 also has the most amount of repetitions. 3 is close, there's 7 of those, but there's 8 2s, so 2 is also the mode, and it's the only one. Note that even though 1 is repeated 4 times, 3 is repeated 7 times, note that they are repeated, that doesn't make them the mode. It is the most repeated. There's only a tie if there were also 8 3s. Then I would have both 2 and 3 are both modes. So that would be the mean, median, and mode. All right, so those are going to be our classic measures of center. Now, if we're going to be talking about how to measure the spread of the data, that's a little bit more of a complicated question. Because then the question would be, all right, well, great. You found the mean of 2.52. That's wonderful. But how does the data spread from that? I want another piece of information that tells me not just where the center is, but how the data spreads away from that. Is that 2.52 is the center and it spreads up to 10? Or is it 2.52 and it spreads up to 3? I don't know. I want to know another number that represents that. And there's a few different easy ones we can do. The easiest and most classical representation is just a range. The range is the easiest measure of spread you can do. And the range is simply the maximum minus the minimum. So it represents the spread of your values. If I look at my previous set of data, my largest value is a 5, the smallest value is a 1. So in my previous set, I'd have just 5 minus 1. The range is 4. That's a pretty easy way to measure the range. However, the problem is that it's really influenced by these outliers, these really strange high and low numbers. And it doesn't really do much to say how the data spreads away in a flowing manner. So is there a lot of values close to my mean and that it spreads slowly from there, or does it spread really quickly through those 4 numbers? So I want something better. And that number that we're going to talk about that is better is probably the most complicated one in maybe modules 7 through 10. And that's what we call the standard deviation. The standard deviation is going to be a very important tool for us. It's one of the most important tools in statistics. We're going to use it a lot in this section, in Chapter 9 and in Chapter 10. So you need to make sure that you understand what it is. And in order to help you have an understanding of what the standard deviation is, what I'm going to do is give you a quick example of something first. All right, so say we have 2 people that took quizzes. So say I have, I'll put Jack over here. So Jack took 3 quizzes, and here are his scores. He got a 10, he got a 15, and he got a 20. All right, say I have another person. So Jack's going to be over there. And say I have another person. I have, I don't know, let's say Denise. All right, so Denise has 5 quiz scores. Let's say 10, 13, 15, 17, and 20. What I want to do is try to describe these data sets. However, you may already notice a problem here. If I try to describe just the center of the data set and just use that to describe the data itself, well, Jack has a mean and median of 15, and Denise also has a mean and median of 15 if you calculate these 5. So they share the same mean and median. However, just reporting that number is not valid because they're obviously two different data sets. So we need something else to describe how the data spreads away. Was one person more consistent around 15 or one person less consistent around 15? So there's a few things that we could try to look at. The natural reaction is how far away are my values from the mean to try to see how far do they actually spread. Well, if I do that, if I tried to do just the value minus the mean, so x minus x bar, what I get is 10. It's 5 below the mean of 15. 15 is 0 away from 15, and 20 is 5 above 15. I'm just doing 10 minus 15, 15 minus 15, and 20 minus 15. I could do the same thing for Denise, x minus x bar. She also, remember, has the same mean of 15. 10 is 5 below. 13 is 2 below, so 13 minus 15 is negative 2. 15 minus 15 is 0. 17 minus 15 is 2. And 20 minus 15 is 5. This is what we would call deviation, how far the numbers deviate from my center. Nice. Problem, though, if we stop there, put it all together to see, all right, well, how much deviation total do they have? Uh-oh. Negative 5, 0, and 5, that makes 0. Negative 5, negative 2, 2, and 5, and 0 makes 0. Meaning that there is no deviation. This would also be a problem because then that's trying to imply that all of my values are at the same number, that there's no deviation from the mean. But that's obviously not true. These numbers are not all 15. They're a little bit away, either above and below. So we need something better than that. We can't just add the deviations. Now, there's a couple different ways of dealing with this, and I'm going to first deal with what a lot of people come up with first, and I'm going to talk about why it doesn't work. The first thing people try to do is take absolute value of this, and absolute value is not going to work too well. The reason why absolute value doesn't work too well is for the following reason. Say I just had an even easier number set than this. Say I just had the numbers 1 and 3. Well, the average of this, x bar, if I do 1 plus 3 divided by 2, I get an average of 2. That's the average. Well, if I do each of these minus the average, so if I do 1 minus 3, or 1 minus 2 rather, and then I also do 3 minus 2, and I do the absolute value of each of these, which just makes the number positive instead. 1 minus 2 is negative 1, which makes it positive 1. 3 minus 2 is 1, which makes it 1. And if I add these together, I get 2. Nice! No more 0. But what if I messed up somewhere? What if I accidentally found the mean and I made a mistake somehow? I did 1 plus 3 divided by 2, and I got an average of 2.5. Average. But let's see what would happen if I try to find that number away from my original values. So 1 minus 2.5 and 3 minus 2.5. Whoa. Absolute value. All right. If I do each of these, well, 1 minus 2.5 is going to give me negative 1.5. Absolute value makes it positive. Gives me 1.5. And if I do 3 minus 2.5, what I get is 0.5. Add these together, I also get 2. Uh-oh. What this is then implying is that I found a different average that has the same distance or deviation from my numbers, which I don't want. I want one average that is the best number to describe the center of this data. Any other number that would be reported as an average does not do as well describing how far the values deviate. So just doing an absolute value is problematic. What we're instead going to do to make these positive is square them. So we're going to do my difference squared. So negative 5 squared gives me 25, 0, and 5 squared gives also me 25, a total of 50. And I can do the same thing over here with Denise as well. X minus x bar squared. So 25, negative 2 squared is 4, 0, 4, and 25. That's another way of making all these values positive. Add them all together, this gives me 58. Nice, I have two different numbers now. Now we're getting closer and closer to describing these values differently. Now, what I do need to keep in mind is that Denise has 5 numbers. Jack only had 3. So I also need to try to keep in mind that this is trying to describe a different set of values. For Jack, since this 50 describes just 3 numbers, what I'm going to do is take an average of that. Same thing for Denise. This 58 describes 5 numbers, so I'm going to take an average of that. If I do 50 divided by 3, 50 divided by 3, I get about 16.7, approximately. And if I do 58 divided by 5, what I get is 11.6. Even better. Now this is showing that Denise has less deviation than Jack. Jack's numbers tend to deviate a lot more than Denise does. Her numbers are a lot more consistent around that center value. Now we're almost done. The only problem we have to take care of is the one that we introduced ourselves. That squared that we put in here in both these instances, we need to remove. Essentially what we've done is tried to say that the distance here has a distance of 11.6 or 16.7. However, the units have now changed because I squared this. If these were quiz scores, like 10 points, 13 points, 15 points, I have found a distance of 11.6 points squared, or 16.7 points squared. If these were feet, measuring like distance in feet, then my value would be in feet squared, which is describing an area, completely different dimension. And so we need to adjust for that. Since we introduced a square, what we need to do is do the opposite of that. So we need to do a square root. If we do a square root, we get back to our original set value. So 16.7 square root. And we get about 4.08. And for Denise, if I do square root of 11.6, I get 3.41, approximately. So we'd say that she has an average deviation of about 3.41 points, and Jack has a deviation of about 4.08 points, indicating that they both have the same average, but Denise's values don't spread as much compared to Jack's. And that's because we have a lot more information for Denise, so we can more accurately say where the mean should be. That entire process is the science behind a standard deviation, like where it is coming from. The formula for a standard deviation, we usually use the letter sigma to represent it. It looks like an O with a growth. To find the standard deviation, the formula looks like this. It's a big old square root of the sum of x minus x bar squared divided by n. That is the formula for a standard deviation. It looks a lot more complicated than really what it is. That's why I broke it down first. You take each value, you subtract away the mean, and you square that result. Then you sum those up. This is the sum of the squared deviations. So the sum of all my values from the mean squared. And then you divide that by n to find the average of those, and then square root it because that squared exists. We need to get back to our original dimension. If you neglect to do that squared, we sometimes call that the variance. You seldom see that, but that's just the sum of all my values minus mean squared divided by n. This would be the variance, which is what we had before we took the square root. And that's also used in the same way that standard deviation is, where the higher it is, that implies it deviates more. However, it doesn't really have as many direct connections because it's in a completely different dimension. So, more annoying. You will definitely see the standard deviation a lot more. I will say, though, for our cases, we're only going to work with standard deviation for smaller data sets, which brings us to an example. Price of a jar of peanut butter, 5 stores, was these 5 values, and find the standard deviation. Now, we have a few-step process for this, and I'm going to write down the formula for standard deviation again, so I can identify the process that we're going to work through here. All right, so the formula is the sum of all my values minus the mean squared divided by n. Now, the first thing you're going to do is find the mean. That's the first thing we need to do here. Then, what we're going to do is find the difference of the mean squareds, so the squared differences. That's the second step we do. Then we average those. And then fourth, take a square root. Those are the 4 things that we'll do. Those are the 4 exact things I did before in the previous example. Now, I said earlier to keep in mind that we did this data set earlier, and if I recall, the mean was 3.68. Yes, 3.68. We calculated that previously, so we'll just mark that down right now. So we'll say x bar is 3.68, or mu is 3.68. Sometimes you'll see this formula with mu instead of x bar. That's technically more correct, but doesn't really matter. Not for our purposes. All right, so we have our mean, and that value we need to use, because what we need to do is take each of our numbers here and find the square differences. We have 3.68 and 3.29 and 3.58, 3.79, 3.75, etc. So we need to find all the square differences. So we're going to do our number 3.29 minus the mean and square that. And we're going to do the same thing for 3.59 minus the mean squared, and do that for all my values. One thing to note here is that it doesn't matter what numbers you do first, what numbers you do last. I like either in order here of these 5 values or even inside the parentheses, because you're going to square the result anyway. So if you did the mean minus each value and squared that, you would get the exact same number. Because you're going to square the result, it's just going to become a positive version of whatever it was. All right, so we're going to find what each of these are, and we're going to sum them all up and take the square root. So this one's not going to be too nice just because it has decimals. So 3.29 minus 3.68 gives you negative 0.39. Square that, and you get 0.1521. And we do that for each of these. So 3.59 minus 3.68 squared gives you 0.0081. If you're doing all of these each at once, make sure you are careful with parentheses, because it does matter. 0.0121, 3.68 squared, 0.0049, and lastly 3.99 minus 3.68 squared, and 0.0961. So we found the mean, and then we took all the square differences. Now what we need to do is average all of these. So we're going to add them all up and divide by how many there are, which if you recall, 1, 2, 3, 4, 5, there's 5 numbers. So 0.1521 plus 0.0081 plus 0.0121 plus 0.0049 plus 0.0961 gives you a sum of 0.2753. and we divide that by 5. We get 0.05466. So that would be the sum, or the average of the squared deviations. Note that I am not rounding at all at any point of this. I am keeping all my decimals as long as I can. You should always do that for everything that you do. Now we're almost done. We've averaged them. Now we just need to take the square root. So what we need to do is take the square root of 0.05466, and then I'll round at the end. So square root of 0.05466, and this one, this was in dollars, so I'll also round to dollars, 0.23. That would be my deviation. That's explaining how far the values spread away from the mean. All right. Now, when you look back at everything we did, yes, this looks like a long process. There was a lot that was done here. However, if you keep this organized, if you keep it in order, like the recommendations that I have here for finding the mean, then do the square differences, then do the average, basically working from the inside of the square root out, it'll be a lot easier to manage. Do a couple examples of those, and you'll start to get the hang of it. All right. Now, what we're also going to talk about is another way of representing the data, both with center and with spread. Well, one of them we've already kind of covered. What we're going to talk about is what we refer to as the 5-number summary. This data set will look familiar. We did this with a histogram earlier. But what we're going to do is find a 5-number summary for this. A 5-number summary is, as you may expect, it's 5 numbers. And it's 5 numbers to help represent both the center and the spread of the data. The 5-number summary is set up of these 5 numbers specifically. It's made up of first the minimum, then the what we call quartile 1. So minimum, quartile 1, or the first quartile, the median, quartile 3, or the third quartile, and the maximum. 3 of these we already should know. We know the minimum, check. We know what the maximum is, check. Those are pretty obvious, the lowest and the highest number respectively. And we know how to find the median, check. We do so using the locator of n divided by 2. The 2 new ones are quartile 1 and quartile 3. The reason why we call these quartiles is because what they're supposed to do is divide the data into quarter pieces. Specifically, quartile 1 has 1/4 of the data below it. If you think about it like a number line here, there's 3 quartiles, the median also being one of them, and you only need 3 cuts to divide this into 4 pieces. 1 cut directly in the middle, that cuts it in half, and then 2 more cuts makes you have 1, 2, 3, 4 pieces of this line. This one here being Q1, this one here being the median, and here being Q3. The median is also sometimes known as Q2. Well, if you notice what happened, the median was directly in the middle. It cut it in half. The first quartile cut off the first quarter. So we're going to find the first quartile by doing n divided by 4, or 1/4. So you could also do 0.25 times n. That's another way of doing it. Same thing for median. You could also do 0.5 times n if you're more comfortable with doing decimals and fractions. For the third quartile, it has 3/4 below it, or 3/4 of n. Or if you like decimals, 0.75 n. I know some people like the decimals definitely because 1/4 is 25 cents, 2/4 is 50 cents, 3/4 is 75 cents. Maybe it's a little bit easier to understand there. Notice that these are just different locators, and we're still going to follow the same process that we did for the median. If the locator is a decimal, you round up, and that's the number you want. If the locator is a whole number, then you take that number and average with the one above it. And that's what we're going to do here. We're going to use the 5-number summary to find the 5-number summary for, we're going to use these definitions to find the 5-number summary for this data up here. All right, so erasing all this so I have a little more room. Okay, so if I work through this, first the minimum, that's the easiest one. The minimum here is the lowest number, it's 140. Done. The maximum, also pretty easy. The largest number, 460. Done. The other three take a little bit more work. For Q1, what I'm going to do is take the total amount of numbers, which is 36. That's how many numbers there are. Whoop. That's how many numbers there are in that data set. So 36. So if I do 36 divided by 4, what I get is 9. Using the logic from median, since that's a whole number, I want to take the 9th and the 10th and average those. The 9th number here, if I look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Thankfully, they're already in numerical order. The 9th is 250, and the 10th is 260. So Q1 is going to be the average of those. 250 plus 260 divided by 2 gives you 255. And that's Q1. For Q2, or the median, I would do the same process. Here I would do 36 divided by 2. That gives me 18. So I want the 18th and the 19th number and average those. So that was the 10th. So 11th, 12, 13, 14, 15, 16, 17, 18, and 19. So 18 and 19. So that will be 305 plus 310 divided by 2 gives me a decimal of 307.5. And we're almost done. Last one we need to find is Q3. Well, if I do 3/4 of that, 3 times 36 divided by 4, what I get is 27. So I want the 27th and the 28th. And divide that by 2. It's really nice that all three of these work in the same way. Just use a different number. Now again, if you prefer to use decimals, you could always do 36 times 0.75 and you get 27. Works the same way. Either way, we already know that this was the 19th. So 20, 1, 2, 3, 4, 5, 6, 7, and 28. So 345 plus 350. Cut that in half. You get 347.5. That would be my 5-number summary. So note that it did take a little bit of calculation to do. However, that's definitely the best way to do it. Just find the locator of where it should be, and then you can look up in the data to see where that is, either in a list of data like this or using a frequency list, like we did earlier with the median. You can do the same stuff with quartiles. Now what this does is it measures both the center of the data and it measures the spread by representing the other 4 values in the 5-number summary. If you recall, when I first drew the picture of it, I explained it as a number line that gets cut into 4 pieces. Each piece here is representing 25% of the data. That's what each of these pieces are representing. So it's both showing where the center of the data is and how the data spreads away from that, both above it and below. So that's another really good way of representing the spread of the data. And it tends to be really good if data is skewed, or it has data that's really low or really high, whereas the standard deviation would get really influenced by that. Also, it takes a lot less calculation to do for this. Standard deviation for this would mean you'd have to do for all 36 numbers, which would take quite a bit of time. We're never going to ask you to do it for that many values, but know how to do it for a small data set. All right, last thing we have. Now, when we were talking about graphing, we talked about bar graphs, we talked about pie charts, we talked about histograms, and I said there was one other graph you can have, but we're going to save it to later. And that graph is called a box plot. A box plot is just a graphical representation of a 5-number summary. So a box plot is just a graph of the 5-number summary, or 5-num sum. That's all a box plot is. And you may have seen them before. Box plots tend to look like this. You have a box in the middle that has a line somewhere, and then you have what we call whiskers that go above and below it. This would be an example of a box plot, and it would be sitting above some number line. That is what we're looking for. And if you notice, the box plot is made up of 5 vertical lines. 1, 2, 3, 4, and 5. Those 5 lines representing my 5 numbers in the 5-number summary. The minimum, Q1, the median, Q3, and the maximum. So the best way to make a box plot is to find the 5-number summary, put them above a number line, and making 5 vertical slashes, and then connecting to make the box plot itself. You may have also heard of box plots as referred to box and whisker plots. We tend to try to shy away from that terminology, however, because sometimes you can have a box plot that doesn't have whiskers, or you could have what we call a truncated box plot, something that just looks like this. This would be a box plot. This is indicating that the minimum, Q1, and the median are all the same number, because there is no other number here. They all just kind of got squished in, as if some big old hammer came in and just pushed it all in here. So sometimes you may not even have whiskers, sometimes you may just have one. We try to shy away from calling it a box and whisker plot. Now to do that for our data set, it says to find a box plot based on the textbook price data set from the last try it now, which is the one we just did. And all we need to do is report what the 5-number summary is again and just graph those down. So we had 140, that was our minimum. Then we had 255, 307.5. So 255, 307.5. Then we had 347.5 and 460. Right? Yeah. Okay. So those were our 5 numbers. Now to represent this as a box and whisker plot, or box plot rather, what we're going to do is make a horizontal line to represent our x-axis and put these values down. So I'll just make this nice and easy. Let's do 100. Then let's do 150, and we'll just go up by 50s. 200, 250, 300, 350, 400, 450. All right, that should be nice and easy to represent these values. Now, this is the cost, or the money, and we're going to make a graph, so we should have a title. So this is textbook costs. So title for the plot, and then we can put our values in. 140 is a little bit south of 150, so right there. 255 is right above 250, so right there. 307.5 is a little bit above 300. 347.5 is a little bit below 350. And then 460 is a little bit right there. So 5 vertical lines. Then, to make the box and whisker plot, or the boxes and the whiskers, I create the box in the center here, and then whiskers that come away from that to both the maximum and the minimum. This would be a box plot. Now, if you want to put more data here, some more identifiers and labels, that's by all means, go for it. It's a lot better for the reader anyway. So you can put numbers like 140, 255, 307.5, 347.5, and 460 above each of your slashes to make it a lot easier for the reader to know what numbers they are instead of trying to track these below and trying to see what they're on. What you also want to make sure that I sometimes see students try to do not put the box plot on the line itself. That makes it a lot harder to read, particularly for the whiskers. Always put the box plot above the number line. This is also true if you want to make comparisons. You can make one box plot. Maybe this is for one set of data from one college. Maybe I have another college I want to put above it. So then I can compare back and forth to say, all right, well, this one has a higher median. This one has a lower median. This is 25% of the data between 140 and 255. And that is less than the other 75% of some other college. I can compare box plots back and forth. And you'll particularly see this kind of stuff if you're in any medical degree or anything that has to do with anything medical. Box plots are very common to do for a long time series, for a long time strain of data. You'll see a lot of box plots, usually vertical, all put next to each other in comparison pieces. Something like a box plot here, another box plot here, another box plot here, another box plot here, and you can just compare back and forth to say, all right, well, that's where the median is, and that's how the median has changed over time, and that's how the data itself has spread. So a lot easier to compare and look at. Sometimes you'll see box plots vertical. Most of the time we'll draw them horizontal because it's a lot more room there. You only really need to be vertical if you have a lot of box plots. But that's just if you tend to see them. All right, with that said, that's everything for Module 8 for describing data. What we talked about were graphs, so we talked about how to make a bar graph, a pie chart, a histogram, and now also a box plot. And we talked about ways of measuring the data, both the center of the data using mean, median, and mode, and the spread of the data using the standard deviation and the 5-number summary. That's a lot of content. Now, I definitely recommend rewatching parts of this if you ever need to, but at this point, go and try your hand at the homework and the quiz for this section, see how you do, and I hope everything goes well. With that said, that's everything for this video, so I hope you have a nice day.